Well, welcome to the Higher Truth Show. I want to thank the hunters for sending me this article. And remember, about 6 months ago, I did a video on the strange and mysterious particles that were flying out of the South Pole. These strange and mysterious particles were high-energy neutrinos. And of course, they hinted that we have to come up with newer physics, a new paradigm of physics. We have to rewrite physics to explain the existence of these high-energy neutrinos. And we attribute it to alpha particle collisions occurring in the magnetosphere close to Earth. The sun, this article by Quanta magazine is echoed and mirrored by a couple other articles that we'll discuss at some other time. I'd like to go through this article. It's kind of longer than it needs to be, so I'm going to try to cut out some of the crap. But this is really another explanation of what we're seeing in the solar system as changes in the solar system that are being covered up and mysteriously clouded by astrophysicists. And I do want to stay, because I'm calling out some names today. I do want to say that I feel sorry for scientists, because they're basically at the whim and the control of certain people, certain entities that fund them, that employ them, and also some of the information they may find can be classified as national security. But the title of this article, "The Sun is Stranger Than Astrophysicists Imagine." Again, does that sound familiar? The sun radiates, they say, far more high-frequency light than expected, raising questions about unknown features of the sun's magnetic field and the possibility of even more exotic particles. Now, the problem with that paragraph is that we've been measuring gamma radiation in the sun since about 2008, and currently there is more than just Fermi satellite measuring gamma radiation. So when they talk about there being far more gamma than expected, then that should have been measured 10 years ago. And this article should have been written 10 years ago when we first measured gamma radiation. And we'll go on and talk about this. This article, written by Natalie Wolshover, is very confusing because it fails to identify several things that we know cause gamma radiation. And the major source of gamma radiation is particle collision, but inverse or Compton scattering or even Compton scattering of electrons also creates gamma radiation. So when you have an article explaining an increase in gamma radiation and electrons are completely taken off the table, things do become mysterious. Also, when you ignore the tenfold increase in cosmic rays that are now swarming in and through our solar system, things become mysterious. But when you shed the light on those two elements of gamma ray production and the corona of the sun, then all of a sudden the mystery is taken away. But we can't talk about those things. There is a gag order or a very, very strong influence to keep people from talking about that which is really logical. But here Natalie writes, "A decade's worth of telescope observations of the sun have revealed a startling mystery." So again, they're admitting they've been looking at gamma rays for 10 years. Gamma rays, the highest frequency waves of light or photon energy, radiate from our nearest star 7 times more abundantly than expected. Now wait a minute, if that was the case, why didn't we hear about it 10 years ago? Stranger still, despite this extreme excess of gamma rays overall, a narrow bandwidth of frequencies is curiously absent. In other words, certain wavelengths of gamma have gone down and certain wavelengths of gamma have gone up. And this has caught people by surprise. But we've been We've been taking and photographing pictures in different wavelengths of the sun, of the corona, of the solar system, of galaxies. We've been doing that for a while. The surplus light, she writes, the gap in the spectrum, and the other surprises about the solar gamma ray signal potentially point to unknown features of the sun's magnetic field or more exotic physics. More exotic physics, new physics, different physics. And remember, the high energy neutrinos were using the same exact terminology. We need a new paradigm of physics to explain these. Something yet we have to discover. We're baffled. We're confused. But guess what? All these astrophysicists we're going to be quoting from, they can learn a lot from just talking to one of my subscribers who already know what's going on with the gamma radiation. It's amazing, she writes, that we were so spectacularly wrong about something we should understand really well. I agree. You do understand it really well. You should understand it really well, says Brian Fields. Brian Fields is a particle astrophysicist at the University of Illinois, and he says it's amazing that we are so spectacularly wrong about something we should understand really well. Well, Brian, you guys do understand it really well, and you're not spectacularly wrong. You're spectacularly mum and negligent and blind to all the facts. The unexpected signal has emerged in data from Fermi Gamma Ray Space Telescope, a NASA observatory that scans the sky from its outpost in low Earth orbit. As more Fermi data have accrued, revealing the spectrum of gamma rays coming from the sun in ever greater detail, the puzzles have only proliferated. No, sorry, the bullshit has the only thing that's been proliferating, and the number of neutral helium cosmic rays. The unexpected signal has emerged in the data. It's like it's always been there, but it's suddenly, because we looked at it more carefully, it emerged. Sorry, we've had this data. We've had, it's like taking a thermometer and then finding it 10 years later, finding that the temperature of the sun has gone up. Then you're like, wow, our predictions were wrong. It has nothing to do with predictions. We're talking about comparing data. And when you start talking about pre-data predictions, then it becomes even really more confusing. So she's already quoted one astrophysicist, Brian Fields. We just keep finding surprising things, says Anika Peter of Ohio State University, another astrophysicist from another college. She co-authored the recent white paper summarizing several years of findings about the solar gamma ray signal. It's definitely the most surprising thing we've ever worked on. You just now analyzing 10 years of data? What did you store it somewhere and then just decided to pull it out and look at it? Not only is the gamma ray signal far stronger than a decades-old theory predicts. No, let me rephrase that for you and get it more correct for you. It should read, not only is the gamma ray signal far stronger than decades-old data, it also extends to much higher frequencies than predicted. No, much higher frequencies than recorded or previously recorded. And it inexplicably varies across the face of the sun and throughout the 11-year solar cycle. No, it's not inexplicably. It's easily explained. Then there's the gap, which researchers call a dip, a lack of gamma rays with frequencies around, get this, 10 trillion hertz. That's a lot of hertz. The dip just defies all logic, says Tim Linden, eighth and now a third astrophysicist from Ohio State who helped analyze the signal. Fields, who was involved in the work, said they've done a great job with the data, and the story it tells is really kind of amazing. Well, if they've done a great job in the data, why are they talking about pre-data theory? Why aren't they talking about early data versus later data? The likely protagonist of this story, says Fields, are particles called cosmic rays. Ding. Typically protons. Well, there's your problem. If you're looking to explain the energy by proton cosmic rays, well, you're in trouble. Why aren't you looking at other cosmic rays? Oh, we can't. I forgot. You're not allowed. So let's go back to this paragraph by Mr. Fields. The likely protagonists of the story are particles called cosmic rays. Typically protons, they have been slingshotted into the solar system by the shock waves of distant supernovas or other explosions. Well, Mr. Fields, I would like to call your attention to the Pamela experiment. Pamela, spelled just like it sounds, found out that we're not going through a shock wave of a supernova. If we were going through a shock wave of a supernova, we would actually be going through what? A supernova. And if we were actually going through a supernova, I wouldn't be sitting here making fun of your article. Physicists do not think the sun emits any gamma rays from within. Nuclear fusion in its core that does produce these, but they scatter and downgrade to lower energy light before leaving the sun. However, in 1991, there's a bunch of physicists, who I'm not even going to talk about, hypothesized that the sun would nonetheless glow in gamma rays because of cosmic rays that zip in from outer space and plunge towards the sun. Occasionally, the Delaware trio argued a sunward plunging cosmic ray would get turned around in the magnetic loops. Why? Because it has a charge. And they would turn around at the last second by the sun's loopy, twisty magnetic field. Imagine the proton runs straight towards the sphere, and at the last second it changes direction and comes back at you. On its way back out, the cosmic ray collides with gas in the solar atmosphere and fizzles in a flurry of gamma radiation and subatomic particles. But why does it have to collide on the way out? Why can't it collide on the way in? Well, nobody is going to talk about that. Based upon the rate at which cosmic rays enter the solar system, the estimated strength of the sun's magnetic field, the density of the atmosphere, and other factors, which we're not going to talk about, Seckel and colleagues calculated the mirroring process to be roughly 1% efficient. They predict a faint glow of gamma rays. I have no idea what that means by 1% efficient. Yet the Fermi telescope detects, on average, 7 times more gamma rays coming from the solar disk than this cosmic ray theory predicted. Now, wait a minute. What about your 10 years of observations? Is Fermi's detecting a 7 times increase in data, and 7 times increase in measurements, or is it 7 times more in increase in the theory? Well, we should have no theories to talk about. We should be talking about the data. And they write, the signal becomes up to 20 times stronger than predicted. Again, here we go, for gamma rays with the highest frequencies. So, we found that the process was consistent with 100% efficiency at high energies, Linden said. Every cosmic ray that comes in has to be turned around. This is puzzling, since the most energetic cosmic rays should be the hardest to turn around. Well, yes, the faster, the hotter, the more resistant it will become to the magnetic influences. But notice how they leave out neutral helium and electrons. So the Gaussian model says nothing about any dips. Also, missing energy. It's difficult to imagine how you would end up with a deep, narrow dip in gamma ray spectrum by starting with cosmic rays, says one guy. We have a smooth spectrum of energies, it's supposed to be. It's hard to get dips in general, he said. It's much easier to get bumps than dips. If I have something that comes out of the sun, he says, okay, that's an extra channel. How do I make a negative channel out of that? Oh, here, my subs will tell you: absorption and deflection. Okay, thank you. Perhaps the strong glow of gamma rays reflects a source other than doomed cosmic rays. Here we go, like the high energy neutrinos, another source, another paradigm. But physicists have struggled to imagine what this could be. They've long suspected the sun's core might harbor dark matter, and that the dark matter particles, after being drawn in, trapped by gravity, might be dense enough there to annihilate each other. But generally, like particles do not annihilate. It is the opposite. Charged particles that annihilate. A typical annihilation would be where a positron runs into an electron. How could gamma rays produced by annihilating dark matter in the core avoid scattering before escaping the sun, and then cause an increase in gamma rays? Well, the bottom line is it's not happening. You're using theory to explain something, and you're ignoring data. Attempts to link the gamma ray signal to dark matter seems like a Rube Goldberg type thing. I have no idea what that means, a Rube Goldberg type thing. Some aspects of the signal do point to cosmic rays and to the broad strokes of the 1991 theory. Will you quit talking about the 91 theory? Start talking about the 2008 measurements. For instance, the Fermi telescope detects many more gamma rays during solar minimum. Well, that's because there's more particles, and we are at a space-age high in neutral helium, lithium, and electrons. A space-age high, the highest we've ever seen. So the fact that Fermi telescope is picking up more gamma rays than ever before, especially than been theorized, well then, that's to be expected. It's to be predicted. But when you don't talk about record amount and record density of neutral helium, when you leave that off the table, well, yeah, then we get real mysterious, don't we? Well, the phase of the sun's 11-year cycle, when its magnetic field is calmest and most orderly, is solar minimum. That's when we get the most cosmic rays, because the sun does not and cannot push them out towards the bow shocks zone. So they write, this makes sense. Experts say if cosmic rays are the source, then in solar minimum we would see more gamma radiation, which is what we find. During solar minimum, more cosmic rays can reach the strong magnetic field near the sun's surface and get mirrored or turned around, instead of being deflected prematurely by the turbulent tangle of magnetic field lines that pervades the inner solar system at other times. Yes, they do get deflected when the sun is stronger, because the sun shoots out CMEs, which kind of push out these cosmic rays and push them around and redirect them around our solar system. On the other hand, the detected gamma rays drop off as a function of frequency at a different rate than the cosmic rays. Now wait a minute, if cosmic rays are a source, the two rates would be expected to match. Boy, that's a very vague statement, because they're not referencing any data, they're not telling you what wavelengths, and if the gamma ray drops off as a function of frequency at a different rate than the cosmic rays drop off, I'd like to see what the heck they're talking about. Because one minute they're saying we get more gamma with more cosmic rays, but now they're saying we're getting less gamma with more cosmic rays. So that kind of contradictory statement is found in anything that is lying to you, because they have to cover their bases with people who know better. Whether or not cosmic rays account for the entire gamma ray signal, says Joe Giacalone, a heliospheric physicist at the University of Arizona. So what, this is like our fifth, sixth astrophysicist now who's jumping in and stirring the pot. And you know the expression, too many cooks spoil the broth. It's probably telling us something very fundamental about the magnetic structure of the sun. No, Joe, it's not. It's telling us something very fundamental about a tenfold increase in neutral particles. The sun is the most extensively studied star, yet its magnetic field, generated by churning maelstrom of charged particles inside it, remains poorly understood, leaving us with blurry picture of how stars operate. No, Joe, it's very clear how stars operate. There's articles, thousands and thousands and thousands of pages about this, and there's pictures of our magnetic field lines that are very specifically mapped. There is nothing that is poorly understood about the sun's magnetism, except maybe what causes our solar cycles, what causes a sunspot. But my subs have already been able to answer that question. Gia Colon points to the corona, the wispy plasma envelope that surrounds the sun. To efficiently mirror cosmic rays or turn them around or wrap them around, the magnetic field of the corona is probably stronger and oriented differently than scientists thought. It is not oriented differently, and it is stronger the closer you get to the sun. Those magnetic field lines are measurable, just like you would take a temperature. They measure these strengths of these magnetic fields in a unit called nanoteslas. But he continues to babble. However, he noted that the coronal magnetic field must be strong only very close to the sun's surface so as not to mirror cosmic rays too soon, not to flip them around or wrap them around too soon, before they've entered the zone where the atmosphere is dense enough for collisions to occur. But hey, guy, collisions are occurring out in space. Fermilab, in previous articles, has said our background sky is aglow with gamma radiation, and we know it's due to two things, and one of them you're never going to tell us about. Collisions, and what else? Compton scattering of electrons. Never going to hear the word electron in this article. And the magnetic field seems to become particularly strong near the equator during some solar minimums, or during solar minimum. These fresh clues about the structure of the magnetic field could help unravel the long-standing mystery of the solar cycle. We've unraveled that mystery. Jupiter has an 11-year orbit, and in every 11 years it aligns with Aquarius, an inbound approach radiant point that then takes debris and slings it towards the inner solar system and creating magnetic sunspots when they hit the surface of the sun. You take a huge iron asteroid and you collide it into the sun. We know the sun collects matter, so tell me what happens when a pure iron asteroid hits the surface of the sun. What happens? You get sunspots. Every 11 years, the whole magnetic field of the sun reverses, says Igor Moskalenko. Igor Moskalenko is a senior scientist at Stanford University who has participated in the Fermi scientific collaboration. That poor guy. We have south in the place of north and north in the place of south. That's the switching of the sun's polarity. This dramatic change, the sun is huge, and why we observe this change of polarity and why it's so periodic, nobody actually knows except for the Higher Truth channel. Cosmic rays, he said, and the pattern of gamma rays that they produce may answer this very important question. Oh, wait a minute, the other guy said it was the magnetic field that was going to answer these questions. Now you're saying it's the cosmic rays. So you guys are already sending us in two different directions, and they're both wrong directions. Why is the sun changing polarity every 11 years? He questions. But there is no good guesses about how the sun's magnetic field might create the dip in gamma ray spectrum at 10 trillion hertz. Is such an unusual feature that some experts doubt that it's even real. Well, if you keep neutral helium a secret and you keep the fact that it's increased in cosmic ray densities by 10-fold increase from one particle per cubic meter to 10 particles per cubic meter, then you can understand just in the background we're going to have more collisions just in the background. But what happens when you concentrate this 10-fold increase in neutral helium? You get even higher densities. But If the absence of gamma rays around this certain frequency is a miscalculation or a problem with Fermi's instruments, no one has figured out the cause. It does not seem to be any instrumental effect, says Elena Orlando, an astrophysicist at Stanford and a member of the Fermi team. So, I mean, boy, how many different cooks are going to stir this broth? When Peter, Linden, and Beacon and their colleagues, I mean, that's 3 astrophysicists right there, Peter, Linden, and Beacon, and their collaborators found the dip in Fermi's data last year. A dip that hasn't existed for 10 years. They tried hard to get rid of it before publishing their discovery. I think there are 15 pages in the appendix of different tests we ran to see whether we were miscalculating, Linden said. Statistically, the dip appears very prominent. And yes, a dip in gamma radiation can be caused by what? Absorption. However, Orlando emphasized that the sun's motion through the sky make the data analysis very challenging. So 1 minute it's the cosmic rays that's causing these anomalies. 1 minute it's the magnetic field that we don't understand at all causing changes. And now it's the motion of the sun, which is very consistent and has always been there. Now it makes everything challenging because the sun's in motion. Well, she should know, they write. She and collaborators discovered the stream of gamma rays coming from the sun for the first time in 2008 using Egret satellite, Fermi's predecessor. So there you go. They're starting to admit, well, yeah, we've detected gamma rays and been measuring gamma rays since 2008. Orlando has also been centrally involved in processing Fermi's solar gamma ray data. In her view, more data is needed. Oh, great. Yeah, I agree. The data you're missing, and you can measure and measure and measure, but the data you're missing has to do with the density of neutral helium and other cosmic rays that you're not even talking about, like electrons. A solar panel malfunction, they say, kept Fermi's telescope mostly pointed away from the sun for the last year, but workarounds have been found just in time for solar minimum. So, a solar panel generates energy. Fermi's telescope spent the whole year scanning the solar system and other galaxies, so it was working just fine. But somehow they just couldn't turn it towards the sun. I bet it had, and that we just don't hear about that missing data. The sun's magnetic field lines are currently curving tidally from pole to pole. If this solar minimum is like the last, the gamma ray signal is now at its most robust. Why? Because there's more cosmic rays. That's what makes this so exciting, Linden says. Right now we're just hitting the peak of solar minimum, so hopefully we'll see higher energy gamma ray emissions with a number of telescopes, which they're not going to tell you about, except for this one, the HAWC, HAWC, the High Altitude Water Cherenkov Experiment. Will take data. HAWC detects gamma rays at even higher frequencies than Fermi can measure, which will reveal more of the signal, more of the gamma ray signal. Scientists are also eager to see whether the spatial pattern of gamma rays changes relative to the 11 years ago. Well, they already have that comparison. And that's where the increases have been detected, because it doesn't match up with what we had in 2008, which was the heart of another solar minimum. Problem is when they tell you the cosmic rays remain positively charged, all of a sudden you're talking about something that is completely and totally false. So how can you arrive at an accurate conclusion when you're not talking about neutral helium, and you're not talking about electrons, and electrons are negatively charged? So if you're not going to talk about negatively charged electrons, and you're not going to talk about the massive increase in neutral helium, how in the world are you even writing an article about this? These clues, they say, could help solve the mystery. There is no mystery. Hawk and scientists hope to report their findings within a year, and scientists both within the Fermi collaboration and outside of it have started to pore over its accruing data already. Since NASA is publicly funded, and well, it's not just publicly funded, the Pentagon funds half of it, anybody can download this data if they want, said Linden, who downloads Fermi's new data almost every day. So that's not true. We've showed you, Mr. Linden, many of NASA's measurements and instruments have been taken down and altered. Let me just give you, for instance, the EVE 3-day diode off the Solar Dynamic Observatory has been taken down. The source, radiation, irradiance measurements were taken down and then put back up, and they showed dramatic changes in those readings. And then you go to SWICS, SWICS, try to find the helium and the lithium data on SWICS so anybody can download data is a misstatement, Mr. Linden. So the last paragraph of this wonderfully entertaining article, which fails to mention some of the most common features of gamma radiation, which is electron scattering and ionization of helium and collision of alpha particles, not protons. So far, I mean, if you leave all of that off the table, you're never going to come to the answers. And why did you leave it all off the table? I have to ask you, why did you leave the electrons and the neutral helium off the table? So they write, the worst that can happen here is that we find out that the sun is stranger, more beautiful than we imagined. Well, yes, that's what they said about the neutrinos flying out of the South Pole. Things are stranger. Our solar system is stranger, more baffling than we ever imagined. No, it's not. It's baffling only when you fail to take the biggest pieces of your puzzle and you hide them under your bed. So, he also said that the best thing that could happen is that we discover some new kind of physics. Yeah, a new kind of physics. That's what we're seeing, is a physics that leaves out data. That's a new kind of physics to me. So let me rewrite this paragraph for you guys, Mr. Linden and Mr. Beacom. Let's rewrite that last paragraph. Instead of writing, the worst that can happen here is that we find out the sun is stranger, let's write this. The worst that can happen is that we find that the sun's data has been kept secret. And the best that could happen is that we discover a new kind of physics? No. The best that can happen is that we throw these bums in jail who are forcing scientists to misrepresent and omit the biggest pieces of these scientific puzzles. And until next time, be prepared, not scared.